operators are constructs used to create expressions with variables and literals. Examples of operators include arithmetic operators, relational operators, logical operators, and bitwise operators. The results of expressions are often stored in a variable, so this is done using the assignment operator, so what we often call the equals sign. So in this example here, you can see we're doing we got a literal 2.5, and then we're using so this is a multiplication operator, so we're multiplying 2.5 with the value stored in a variable y, and the result of this operation will then be stored in a variable x. So you can see here we're declaring x when we're kind of initializing it with the result of this operation. So we do that using this assignment operator. So when you're doing an assignment, there's only certain things that can go on the left hand side of an assignment operator, and generally these are objects that represent a memory location. So basically like a variable, it's where we want to store the result of some operation. So things that go on the right hand side, so we can have variables on the right hand side, we can have literals, that's just literal numbers, and also expressions. So the assignment operator works from right to left in the fact that the thing that's on the right is evaluated first. So it's important to realise with this assignment operator, although we might often say, for example in here, x is equal to 5, that we're actually assigning the value 5 to the variable x, so we're going from right to left. So we take the value 5 and we put it in the variable x. So when you say x equals 5, that's in normal, say, algebra, it's not, it doesn't really, if you just check whether this is, we'd say that's the same essentially. It doesn't really matter, but it does matter when we're doing these operators. So we can say, so we can get the value 5 and we can assign it to the variable x. So now at this point, if we're executing these lines of code, we've assigned the value 5 to x, so because we're going from right to left, when we do this, both of these on the right hand side of the assignment operator, so we'll have 5 plus 5, will obviously give us 10, and then that will be stored in x, so that we can update the value that's stored in a variable. So x now contains 10, and then assuming that we've got two other variables, y and x, we'll do an addition with those, and then the result will go into x. So these top three are all perfectly fine. It's completely acceptable to write that, because again, this is completely, that doesn't really make sense if you're thinking about normal algebra, say. So there you'd say x equals x plus x, so x equals 2x. No, something's gone wrong there, that's wrong. So that, that doesn't make sense. But when we're doing with the assignment operator, this is perfectly acceptable. Again, the value, what's in x, adding it to itself again and storing the result back in x. So next one down, so this 7 equals x, this is incorrect. We cannot store, we can't assign the value to a literal, so we cannot do that. And the same on this, we cannot have an expression on the left hand side of an assignment operator, so that's incorrect. This is actually correct. That's a perfect acceptable operation, x plus 1, but you can see it's useless because we're not actually storing the value anywhere. Normally we want to do something like y equals x plus 1. So you have to be careful, because that won't give you any compilation errors or anything like this, but it's useless. You're doing an operation, but then you're not storing the result of the operation anywhere. So this table shows all the different operators you've got. We've got a normal arithmetic operators we're used to. The modulo, this finds a remainder. These increment by 1 and decrement by 1. So for example, you can do, very common, you'll see x plus plus and that. So if you got a value x and it's got the value 7, you assign the value 7 to it and you do x plus plus. After this, x will be equal to 8. And obviously with the decrement, if you did that, it would be equal to 6. So then this is the equivalence operator, so double equals, so this is different from the assignment operator. So single equals sign is the assignment operator, double equals is the equivalent operator, not equals, greater than equal to, less than equal to. Then we've got our logical operators. So we can do logical and, logical or, logical not, just like we've seen with logic gates. So note they've got the double ampersand, double pipe, because when you see the single ones, these are the bitwise variations of these. So we've got bitwise and, bitwise or, bitwise exclusive or, and bitwise not. So this is where you do the logical operator on each pair of bits, just like we've seen with that when you've got multiple logic gates in parallel. Then we can also do a bitwise left shift and a bitwise right shift. So this is like a shift register. You can get a value and you can shift that left and right. So these are the common operators that you'll be using. So we'll look at some examples now. So here we've got two variables, a and b. So we're using those to store floating point numbers, so we'll use the float data type. So we're assigned on the values 1.5 and 9.0. So you see, it's very, once you've declared your variables, it's very simple. It's just like, using a calculator really. So float c, we'll assign that the value of a times b. So now obviously at that point c will have the value 13.5. b divided by a, c plus d, e minus c. So you can just build up your expressions using the normal arithmetic operations. We'll look at some of the logical ones now, because here now we're using integers. So now I've got int a is 0, int b is 5. It's just worth pointing out this, you couldn't do this in a real piece of source code, like have these lines of code here, because we've already got a variable called a and b, for example. So if you tried to put int a further on, it'll just give you a compilation error. So this will be a completely separate piece of source code where we're just dealing with integers. So we've assigned a the value of 0, assigned b 5. But when we're doing these logical operators, it's just remember that the logical operators just deal with zeros and ones. So actually, obviously 0 is 0 or false, and anything else, anything other than that is deemed to be true or a 1. So in this example, we've got a and b. So that's essentially a, and because b is non-zero, it's 1. So we obviously get as 0 for c. A or b, 0 or 1 will give us a 1 for d. E equals not a, so you can see a is a 0, so not a will be a 1, so e will end up with a value 1. And then b is non-zero, so it's deemed to be true. So if you do not b, it'll become false, and f will be 0. So just be wary when you're doing the logical operations that you treat the values as, say, zeros and ones, whether they're true or false. So whether there's 0 or non-zero. So I'm looking at some bitwise operators now. So we've got these chairs here. So we've got a and a b. So assuming these are unsigned chairs. So on some compilers you'd have to write in the front unsigned, just for all these variables. So we know the bit pattern of 0 is just obviously all zeros. Bit pattern of 5 is 101 at the end. So when we do bitwise a and b, we're looking at these each pair here. So 0 and 1 gives us 0. 0 and 0 gives us 0, 0 and 1 gives us 0, 0 and 0 gives us 0. Then we've got the OR operation, so we know 0 or 1 will give us 1, 0 or 0, 0, 0. So you can see the, that's like X or X just gives you X. So we've ended up with the same result here. This is exclusive OR. So again, we've got 0 exclusive OR 1 gives you 1, 0 exclusive OR 0 gives you 0, 0 exclusive OR 1 gives you 1. Then this is a bitwise NOT operator, so this is where we just invert all the bits. So obviously A, for a chair is 8 bits, so we've got 8 zeros, so we'll end up with 8 ones, will give us a value 255 in decimal. And then NOT B, which is the same, we just invert all these bits, and that equivalent to 250 in decimal. So that's showing some bitwise operators. Now we'll look at some shifts. So again, we'll start here. We'll assume A has got a value of 1, so we know in binary this is a binary pattern we'll have. 1 to 8, we've got this binary pattern. So we're just, it's very simple. So A, left shift by 4, we're just going to shift this 1 4 places, 1, 2, 3, 4. So it ends up here, what gives us a decimal equivalent of 16. And then B is 128, so obviously the 1 starts in the most significant column. We're going to right shift it by 3 places, so we'll go 1, 2, 3. And again, we end up with the same value, 16. So this looks a bit more of a complicated expression. This is very common in embedded systems. So assuming we got our value C, so we work from this code here, we know that with C's ended up with this bit pattern. So I'll write down, so this is C, so this top line represents C, and it's going to be bitwise OR with 1 shifted 2 places to the right. So we've got a 1, so we know 1 is obviously that. Shift it 2 places to the right, we'll end up getting this. So this line represents 1 shifted 2 places to the left, sorry. Then we're going to do bitwise OR, so we end up with 0, 0, 0, 0, 0, 0, 0, 1, 1. We'll keep going along each one of these bits, and we'll end up with that pattern. What's the equivalent to the decimal value 20? So you might wonder, why is this common in embedded systems? Because what this does, this is like a bit setting procedure. So what we've actually done, if you call this n, that the number what goes here, we call it n, we just set bit n in that number. So you can see, if you look at the result here, what we've ended up with, it's basically the same as the input that we put in, so C here, and we just set the second bit. So these two numbers, so C and the output, are just different by this 1 bit. So what this kind of operator does, it's very common, it just gets the value stored in C, and it sets the second bit in there. So if you did, for example, if we change that to 3, we'd end up, that will just be 0, and that will be a 1. So the third bit will be set. And then if, for example, that was 7, we'd end up getting the original value C, and the 7th bit would be set. So that's a bit setting. This one here is how we clear a bit. So again, we'll start with C. So this top line represents C, and the second line represents this 1 shifted left by 4 places. So I have 1, 2, 3, 4. Now we're going to do the bitwise NOT. So we invert each one of those bits, And then when we do the bitwise AND, we'll see that ends up clearing that bit. So we end up with a 0 here. That gets ANDed with this 1 to give us a 0. So we've taken our original value of C and we've basically set bit 4 to be 0. So these two are very common in embedded systems, so setting a bit and clearing a bit. So when you're doing operations, it's very important to consider the precedence of the operators. So this just determines which order we carry out the operations if there's multiple operators in the expression. So kind of simplified picture. So the most kind of precedent ones are the brackets. Then we've got the bitwise NOT and the logical NOT. We've got multiplication, then division, and modulo, and then addition and subtraction. So these are the, so it's more important. So the kind of most precedent ones at the top. And these here are what we call the associativity. And it's also important because this tells us which order the operators with the same precedence are evaluated. And we'll see an example next. So we can either go right to left or left to right. So we'll look at some examples here. So when we wrote this top expression here, we've got 4 over 2 plus 1. So that will actually come out to be 3 because the divisions are most precedent. So this will take place first, then we'll add it to 1. And it's obviously different when you put brackets in. So the brackets then are the most important. So we do those first. We do what's in the brackets first. So we'll end up then doing 4 over 3, which gives us a 1.33. So it's often useful just to put brackets in. And in this situation, in most times I would just put brackets there just to be on the safe side. And then for example here, we've got chair C is 0, chair D is 5. So in this case, the bitwise NOT is we'll do that the first. That's got the highest priority, so we'll do NOT C first, and then we subtract D from that. And then this highlights the associativity of it. So for addition and subtraction, we go left to right. So in this case, when we've got multiple operators of the same precedence on the same line, we work for, in this case, left to right. So we'll do the left one first. 8 minus 3 obviously gives us 5, and then we'll do 5 minus 2 to give us 3. So this will not give us 7. That's not correct. So in this case, we do because the associativity is left to right, do the left one first, and then we'll do with the right one.